I want to return now to a discussion of wave propagation, this time in higher dimensions. So here is our box of wave. It's a wave propagating in 3 dimensions. The wave is, in the first instance here, propagating purely in the z direction, and we are looking at a cross-section of the wave here in the xy plane. Now the colors here represent the amplitude of the wave, so it's a sinusoidal wave, or a harmonic wave. Red is maximum amplitude, blue is minimum, and white is sort of crossing the origin there. And so if the wave starts off propagating purely in the z direction, what we see is that the amplitude of the wave on the xy plane is uniform. It's changing in time, but it's always the same no matter where you are in this xy plane. This is the case when the wave is propagating purely in the z direction, and the k vector of the wave, that is the direction of the wave, is purely in the z direction. So kz is the only k vector component of this wave which is non-zero. Now we're going to change the angle of the wave. We're going to introduce an angle, and it's an angle up in the y direction. What that means is the k vector of the wave is no longer just kz, we also now have a component of ky. This has the effect on the xy plane of introducing spatial variation in the amplitude of the wave. We can see that at the bottom here we have amplitude positive and here amplitude negative, and as I propagate the wave, this wave appears to move up in the xy plane. So if we restrict ourselves to thinking about what this wave is doing just in the xy plane, we see some sort of wave propagating upwards in the y direction in this yz plane. And as we increase the angle of our wave, so we make ky larger, then we increase the spatial frequency of the wave propagating upward at this xy plane. We make it larger still, and larger still we have higher and higher spatial frequencies up in this direction. So, to summarize, at this particular z-plane, in fact all the z-planes, what we see is the angle of the wave, as the angle of the wave increases, there's more spatial variation in the y direction, so the spatial frequency in the y direction at this plane increases. So if we can, in mathematical terms, give our plane wave, that is this wave in 3 dimensions, the following form. We can give it the form E, which is the amplitude of the wave. We can imagine it's electric component to the electromagnetic wave, or it could be the amplitude of an acoustic wave. It really doesn't matter. It's just any wave propagating, in this case, in 3 dimensions. The wave can be given as some amplitude times e to the I k dot r, where k is the k vector of the wave, that is the direction the wave is propagating. And we expand this dot product, so we get kx times x, ky times y, and kz times z. And so the components of the k vector are kx, ky, and kz. If kx and ky are 0, kz is non-zero, then the wave is propagating purely in the z direction. And as we increase ky in this example here, then the wave starts to propagate upward at an angle in the positive y direction. So increasing the angle means increasing ky. For a single plane wave, which is the situation we have here, a single plane wave with a single frequency, an angle with respect to the z-axis gives a single spatial frequency for a plane taken at any value of z. So that's what we saw here. That for this particular plane of z-plane here, in the xy direction, taking a plane at some value of z, what we have is a single spatial frequency, in this case a spatial frequency in the y direction, due to the increase in ky. So let's look at this a little bit more closely. So we'll consider a harmonic wave with amplitude E0 travelling in direction given by this k vector, and our wave, as before, is written like this. Let's think about the angle of the wave with respect to the z-axis. So here's our axis system, x, y, and z, and we're going to consider just small angles, theta x and theta y. So we're not going to consider really big angles, just small angles to make the maths a little easier. So here's our k vector, k, and it has components in the x, y, and z direction. We can project it down onto the x-axis to find the value of kx, and we can project it onto the y-axis to find the value of ky. And there are corresponding angles, theta y and theta x, associated with these values of kx and ky. And the small angles can be given by theta x is approximately equal to kx on k, and theta y is approximately equal to ky on k, where k, the magnitude k, is just given by the sum of the squares of all the different kx, ky, and kz. So this means that in a z plane, so we can just take z equal to 0 for convenience, but it really doesn't matter if you choose a different value of z. The wave amplitude is given by this. We're going to set z equal to 0, and then we have the wave amplitude, if we expand here, is equal to e to the I kx times x and e to the I ky times y, or we can write this in terms of the angles. So we can replace ky by theta y times k and kx by theta x times k. And this is actually a really profound statement. If we have a harmonic wave traveling at some angle with respect to the z-axis, then at any plane in z, there is a harmonic variation of the wave in the xy plane. So that's what we saw in this animation previously, but now you can see it mathematically, that if you look in the x direction, if you have some angle, some value of kx which is non-zero, then you have some spatial variation of this wave in the x direction, and similarly for the y direction. And this harmonic variation has spatial frequencies given by kx and ky in the x and y directions respectively. And you can see that straight away by considering this equation here. If you took a Fourier transform of this, then the frequency that would pop out, the spatial frequency that would pop out, if you take a Fourier transform over x, the frequency that pops out is kx, and the Fourier transform over y, the spatial frequency that pops out is ky. And for small angles, then the angle and the kx and ky are linked like this. Therefore, the spatial frequencies, that is the spatial frequencies kx and ky of the wave, are mapped onto the angle of propagation, and vice versa. The angle of propagation changes the spatial frequencies kx and ky. So what that means, if you're taking a slice of the wave at some value of z and you're looking at the amplitude of the wave in this slice of z, the pattern that you see, the spatial frequencies that you see in the x and y directions, tell you about the direction the wave was propagating to arrive at that plane in z. So the direction that a wave is traveling with respect to the z-axis determines the shape, the pattern, the spatial frequencies of the waves that you see in that plane of z. And as we'll see, this is a really interesting and useful thing, because what it means is we can now start to use Fourier techniques, that is analyzing the spatial frequencies, to consider how waves propagate. And this is going to lead naturally into a treatment of wave diffraction.